Now, when we consider a Lagrange method to solve partial differential equations of what type? PDF some function of x by z into double z by double x plus some function of x by z into double z by double y is equal to some function of x by z. We always write down directly the auxiliary equations. Dx upon coefficient of p, that is double z by double x. Dy upon coefficient of dz by dy, dz upon the right-hand side. And then we see that in this method, mostly the three ratios which are equal to some constant they are pairwise variable separable equations. So we can take any of the pairs, for example, first two pairs, and we will have dx by minus 1 upon minus dx upon minus a plus x is equal to dy upon minus b plus y. And the integrals can be directly written. For this, it is ln of x minus a. For this, it is ln of y minus b. And there is an arbitrary constant that can be written in terms of ln c. When the two functions are brought to one side, giving out the arbitrary constant on one side, we see that log of this minus log of this give us minus a upon a minus a plus x upon minus b plus y is equal to log of c1. So we say that removing log, you get this solution. A relation between x and y only. So we go for a relation that includes z, otherwise our system will not be complete. So we go for the last two ratios, from where we see that the integral of this dy upon y minus b is ln y minus b, integral of dz upon z minus c is log z minus c plus log c. So exactly in the previous way, we get minus b upon minus b plus y upon minus a plus z, c plus z. And we write down general solutions as this. Remember, somewhere before we said that we have this kind of solutions, or we use by solving the system equation, we get this, or we are given surface equations in terms of an unknown function, we get a differential equation of this type. So this is the solution of the differential equation. And this differential equation is obtained from removing the unknown function or arbitrary constant from this. So we can combine these two into one function, an unknown function of these arguments that appear as integrals. So this comes as the first one, this comes as the second one, not necessarily written down in the same sequence. A simpler problem, x into dou z by dou x plus y into dou z by dou y is equal to z. Auxiliary equations dx upon x, dy upon y, dz upon z. First to give ln x is equal to ln y. Last to give ln y is equal to ln z. So x upon y is equal to c1, y upon z is equal to c2 are the two. We also call them solution curves in a space. So one function is this, one function is this, that we place in the one function is this that comes here. Not necessarily in the same sequence. Very simple situation, p plus q is equal to 1. Auxiliary equations, dx upon 1, dy upon 1, dz upon 1. So we will obtain one solution from one pair and another solution from another pair. X square p plus y square q is equal to z square. A little more complicated situation, but still very simple, because when we write down the auxiliary equation, dx upon x square, dy upon y square, dz upon z square, and we see that the first pair tells us after integration minus 1 upon x is equal to minus 1 upon y plus c. That can be written as this. And second pair or another pair, this one combined with this one. So minus 1 upon x is equal to minus 1 upon z, and minus 1 upon y is equal to minus 1 upon z. So we have three solutions available. We can use only those as involved in the unknown function, which contain all three variables x, y, z. So either first and second or first and third. In this case, solutions are very simple, so second and third can also be placed in this. So some situations are very simple, others are not. X square, a similar question has been discussed before. P plus q is equal to sine of x. So you have dx upon 1, dy upon 1, dz upon sine x. Now this is pairwise variable separable. First is sine x से multiply करते हैं, sine x dx is equal to dz, and that gives you minus cos x is equal to z plus c. Whereas first pair dx is equal to dy gives you integral x is equal to y is equal to plus some constant, so x minus y. So एक curve ये हो गया, एक curve ये हो गया. So we can write down this as z plus cos x. So same situation, simple situation. Zp is equal to x, where p, that is dou z by dou x, is involved, but q is not there. So auxiliary equations will have dx upon coefficient of I was telling you that q is not present, that is dou z by dou y is not present. So dx upon z plus dy upon 0, dz upon x. We are not afraid of writing down dy upon 0 because this all is equal to some constant k. Now you can interpret this as dy is equal to, agar main 0 badal down, is equal to 0, that gives me y is equal to c1. Or I can take the 0 on this side. Whereas first and third, and I see that x or z dz variable separable hai, and that gives me solution x square upon 2 minus z square upon 2, 2 multiplied and embedded in the constant. So we have got this solution curve and this curve, and that make us the unknown function y placed here, x square minus z square placed here. A little bit complicated situation. So dx upon y square, but this is a special situation where instead of p we have got p square, instead of q we have q square. So इसमें से we should be writing it as y square p plus x square q is equal to x square y square z square. So dx upon y square p dy upon x square q dz upon x square y square z square. Now we see that in the first pair, q can be cancelled, so that it is x square dx is equal to y square dy. That gives me x cube minus y cube as the first solution curve. Then we have some strange situation. So how to deal with dx upon y square and the z upon this. Because the involvement of p is troublesome. So that is not a friendly situation. So what is being done here? We write down dx upon y square is equal to dz upon x square y square z square, leaving out p at all, in which y square cancel out. X square dz square gives us this result. Similarly, dy upon x square is equal to this, gives us this result. Now, if you want to find a way that how p and q can be ignored, so we make one attempt by allowing it to be k, so that we have dx is equal to y square p, dy is equal to x square q, and dz is equal to x square y square z square. So, of course, each of them is multiplied by k. I take k is equal to 1 and add them together. I can add any two or all together. So if I add these two, so what I have is dx plus dy equals y square p plus x square y square z square. But that does not give me any idea about how to remove p. But generally, this approach is adopted in the book. So I don't recommend this. Leaving out P and Q without any reason. So that's it about first type. And first type, let me remind you that first type means you are given equation of this type, and we write down auxiliary equations, and the auxiliary equations are such that we get pairs of variable separable equations, and we solve those pairs of variable separable differential equations. In the second type, we have similar situation, but the solution that we produce from one pair is used in the rest of the solution. So how the type 1 and type 2 differ from each other? In type 1, when we write down auxiliary equations of this type, we get pairs in which we have variable separation possible. In fact, we get 3 pairs and we can integrate them directly. But in type 2, we may get a pair which can be integrated directly, but then that solution is used to produce the rest of the solution. So in this particular example, dx upon 1, dy upon minus 2, and dz upon 3x squared sine y plus 2x. So first to give us 2x plus dy is equal to 0, that gives us 2x plus y is equal to c1, a structure that is present here. So that first and third ratios are written as dx is equal to dz upon 3x squared into sine of c1, where now sine of c1 behaves as a constant. Take 3x squared, variable separate ho gaye, or since sine c1 is constant, integration ho gayi aaram se, no problem. X square ka integral x cube, or dx ka integral x upon sine c1 is equal to c2. So we can write this solution as what? Sine c1 se throughout multiply kare, that makes it sine c1 into x cube minus z is equal to c2 sine c1. Now on this side, I don't need to change anything, but I know that this is a function of 2x plus y, because c1 is 2x plus y, so sine of 2x plus y is involved here. So this right hand side is a function of 2x plus y, where the left hand side sine c1 and c1 is 2x plus 1, so we put it back, x cube into sine of 2x plus 1 minus z is equal to this. So in this type 2, one of the solution is obtained in the same way as we get a solution curve in type 1. And this first solution is then used to develop other solutions. So compared to the type 2, instead of writing down as solution curves, all the solutions are independently produced, independent solution curves, but now we have dependent solution curves. That is why we write down C2 on one side, which depends on C1, and that dependence is through this sine 2x. So this solution, second solution, is dependent on the first solution. So we write it as in this functional form, and not instead of going to write down x cubed sine 2x plus y minus z comma 2x plus y. This is the way we used to write down the solution in the previous type, but not anymore, because one solution is dependent on the other solution. For example, here again, one solution is produced from one pair, and that is in the form of x plus y is equal to c. So we see that here, third ratio is dz upon z upon x plus y, and x plus y is c1. So z upon c1, and that makes it integrable. Constant है ये, तो ये c1 यहाँ लिखा जाएगा. X is equal to c1 ln z. And since c1 is equal to x plus y, so x minus x plus y ln z is equal to c2. So this function is dependent on x plus y, which is c2 जो हमारे पास आया है, that is a dependent function dependent on x plus y. So this is the difference between first type and the second type. So here I have considered some जो भी सवाल यहाँ मैं डिस्कस कर रहा हूँ, इन सवालों में mostly the questions are from exercises जिनके आपके पास जवाबात तो हैं, but they are not easily obtained. So for your guideline, I have solved most of the problems from the exercises. This question number 4 is a lengthy one. Dx upon this much, dy upon only this, dz upon only this. Last two are simple, where x cancels out, 2 cancels out, dy upon y, dz. So one solution is this, y upon z. And y upon z can be constructed somewhere in the first part, or I write down this as y is equal to c1z. So y is equal to c1z square. And this becomes 2x taken from here, where? From third ratio. So 2x dx and x square minus z square c square plus 1. Now we can write down this as dz upon dx. This is a first order equation. And we see that this is homogeneous equation. Degree of each term involved in the numerator and the denominator is 2. So the method of solving homogeneous equations we use the method of solving homogeneous first order ordinary equations. So z is equal to vx substitute करके जो method homogeneous का होता है वो हमने इस्तेमाल किया. इंटीग्रेशन भी इसके अंदर सिंपल नहीं आ रही. सो इंटीग्रेशन में भी हमारे पास partial fraction इस्तेमाल हो. There can be situations where you go solving an integral after converting a pair of auxiliary equations into variable separable. You may come across any type of ordinary differential equation that you're required to solve. So that is the major difference, and sometimes you will may have very, very complicated problems. One of the problems where situation is in fact zp minus zq is equal to x plus y. And the auxiliary equations are these: dz upon dx upon z, dy minus z, dz upon z, x plus y. And we see that dz upon x, or first pair में से z cancel हो सकता है, and that will give you a solution this type. Whereas if I take first and the last, I see that x plus y is equal to c1. So c1 dx, z dz, so you get this. Sometimes you get very simple situations, sometimes complicated situations. The third type method for solving linear partial differential equations. Here, what we require is that after, for a given differential equation, after converting the differential equation into the auxiliary equation, dx upon xz, dy upon minus yz, dz upon y square minus x square. We use multipliers. And multipliers means we choose numbers of or functions in such a way that we multiply the numerators and multiply the denominators so that you have dx is equal to k times xz multiplier 1 dy. So sorry, multiplier is not here. K times minus yz and dz is equal to k times y square minus x square. Now, if you multiply each side by some function p1 for the dx, q1 for dy, and r1 for dz. And add left-hand side, add right-hand side, and then you have situation of this type. Yeah, the choice of the multipliers is important because that makes it into an interesting form. Here the multipliers are so chosen that once we add the three equations of this type, the numerator is in the form x some function into dx plus some function of dy into dy plus some function into dz divided by that function multiplied by this first denominator, q1 multiplied by the second, and r1 multiplied by the third. So x, y, and z are multiplied, used as multipliers, so that the denominator becomes 0. X squared z cancels, y squared z cancels. When the denominator is 0, the numerator is also 0. And we have this in integrable form. The integral is this. Choose yet another set of multipliers which lead to a situation that when you multiply the denominators with the chosen multipliers and add the terms involved in the denominator, the result is 0. So यहाँ पे y नहीं था, यहाँ पे x नहीं था, तो यहाँ y multiply किया, यहाँ x multiply किया. So y dx plus x dy upon x y z minus x y z. R is taken to be 0. So we have only this part, which is a differential of xy, and this is what comes out. Now, the solutions obtained are independent solutions. They don't depend on each other. So we again write down the result or the solution to the differential equation as an unknown function, which depends on C1 and C2. And we write down the values of C1 and C2 in terms of function of x, y, z. Another such example, use of multipliers, which when multiplied with the denominators in the ratios of written in the auxiliary equation. When added together, they become 0, so that the numerator is 0, and not only 0, it is in integrable form. So the first independent integral curve is obtained. The second choice of multipliers. Now look at the way the multipliers are chosen. मैं अगर लिस्ट डाउन कर दूं यहाँ y square plus z square minus xy or minus xz, and then think about multipliers. Multipliers should be so chosen that things cancel out. If I want to cancel out minus xy, मेरे पास y square है, तो क्या मैं इसको x से मल्टीप्लाई कर दूं और इसको y से मल्टीप्लाई कर दूं, तो मेरे पास वो सिचुएशन बन जाएगी कि एक्स वाई स्क्वायर कैंसिल हो जाए. जब मैं x को y स्क्वायर प्लस z स्क्वायर से मल्टीप्लाई करूंगा, तो आई विल आल्सो गेट x z स्क्वायर, और फिर मुझे इसको z से मल्टीप्लाई करना पड़ेगा, so that x z square is also cancelled. So these are not wild choices, these are calculated guesses. So again, looking at the same, I can work out with only these two. So I choose first multiplier to be 0, so that this goes out of the equation. So once this goes out of the equation, I consider only this. इसमें z की कमी है, इसमें y की कमी है. So I multiply one of them with z, the other with minus z, so that negative, positive, they become 0. So I can produce the result easily. So look at here. एक function, दूसरा function, 2x minus 3y. मुझे इनको ऐसे नंबर से या फंक्शन से मल्टीप्लाई करना है कि जब इन सबको ऐड करूं तो 0 हो जाए. तो इसको 3 से मल्टीप्लाई कर दो, इसको 2 से मल्टीप्लाई कर दो, इसको 1 से मल्टीप्लाई कर दो, या 0 से मल्टीप्लाई कर दो, एज इट इज डन हियर. सो जब तुम फॉर एग्जांपल हियर ये मैंने किया 3 2 और 1, and this is produced, whereas in the first pair इसको x से मल्टीप्लाई किया, इसको y से मल्टीप्लाई किया, इसको 0 से. So पहला वाला solution produce हो गया. So the choice of these multipliers are not arbitrary, they are systematic. Look here, it is a bit more complicated. So I have written down each denominator separately. And then I think about के भाई क्या करें, multipliers किस तरह से choose करें, so that we choose the multipliers always in such a way that the denominator when added together becomes 0, so that numerators when added together is also. So 1 upon x, 1 upon y, 1 upon z removes the squares from these three, and the rest cancel out. So this was something to be seriously considered. So I have discussed that, and that's it for this third. This here are some examples solved in your book. I have reproduced them here, where you have to find surfaces that pass through a given curve. You are given this differential equation. You solve them. After getting a solution, independent solutions, C1 and C2, what you need to do is that you force them to pass through the curve given x plus y is equal to 0 and z is equal to 1. This is equation of a line in 3 space at height 1 unit from xy plane. So you convert them into parametric form. X is equal to t. So y is equal to minus t due to this, and z is equal to 1. And use C1 and C2. So if you consider C1, so x is t, y is minus t, so it becomes minus t squared, z is 1. So C1 is equal to minus t1 squared. What about C2? X is t, y is minus t, so t squared, z is 1, so 2. So you get C2 in the form of 2t squared. Now t squared is equal to C1, so you replace t squared by C1 here and get a relation between C1 and C2. This is the surface that you have already obtained as a solution to the given curve. In fact, 2 independent solution curves. इससे पहले कि हम फंक्शन बनाएं जो कि पर्टिकुलर सॉल्यूशन हो, हमने इनिशियल ये वो कर्व जो है उसका इस्तेमाल किया and C1 और C2 के दरमियान रिलेशन निकाल दी. Once we have found a relation between C1 and C2, इसको हम सब्स्टिट्यूट कर दें इनमें से किसी भी डिपेंडेंट कर्व में. इनफैक्ट C1 की वैल्यू XYZ, C2 की वैल्यू x square plus y square minus 2z, or C is equal to 2. From where do we get this? X square plus y, that is obtained from here, plus y2. And that gives the particular solution. So the idea is that you work out the solution using the usual way, whether it is type 1, type 2, type 3, and independent solution curves return. And then if the solution surface is required to pass through a curve, so from the equations of C1 and C2, apply conditions of the curve, preferably in a parametric form, obtain a relation between C1 and C2, and finally replace C1 and C2 as function of x, y, z into the relation between C1 and C2. So in this way, particular solutions are obtained. And that is all that I want to discuss as a revision. Most of you were in the class, so I terminate the session. It will terminate yourself. Oh, there is time left. There is time left, so I consider another solution. Okay, we are given this differential equation, and we are required that the surface it represents should pass through this curved circle. So you go the usual way, write down the auxiliary equations. From auxiliary equation, use multipliers 1, 1, 1, and get dx plus dy plus dz is equal to 0, because using multipliers 1, 1, 1, the sum of these functions multiplied by the multipliers is equal to 0. So the first solution curve comes out to be this. Then consider dy upon this second and third one, last two fractions. We see that C1 can be written as what? X is equal to C1 minus Y, because Z is equal to 1. Using that to our advantage, फर्स्ट सोल्यूशन कर्व में z की वैल्यू 1 इस्तेमाल करके c1 x is equal to c1 minus y, so that this x c1 minus y z is equal to 1, and we get the equation of this form. What is this? Okay, C1 is not simply C1 is x plus y plus z. So here we have written y minus z minus x. So y minus x minus z is equal to y plus x plus z minus 2x minus 2z. So that this is C1 and minus 2x minus 2z, whereas x plus z is equal to y, so that y minus x minus z is equal to C1 minus 2y. So it's to be C1 minus 2y. What? This whole denominator, C1 minus 2y, can be written as 2y minus C1 dz upon z. And then it becomes integrable, but dependent on the first curve. So as it is dependent on the first curve, we get C2 after integration and replacing back this value of C1. And using the curve through which the surface has to pass, and we get these equations from C1 and C2. And then you have to eliminate xy to get this equation C1 and C2, that we do by squaring both equations and adding them together. So x squared plus y squared is equal to 1. Whereas the other sides are basic algebraic formula used. So x squared plus y squared is equal to 1, x plus y whole square is equal to this, y minus x whole square is this. Simplify, and that is the value of equation relating C1 and C2. And then C1 and C2 substituted in what equation? Okay, C1 has been obtained as some function of xy. Here, x plus y plus z. And C2 has been obtained as this. So in place of C1, x plus y plus z, x plus y plus z. In place of C2, minus x plus y minus z divided by z whole square. And this is the required particular integral. So after these particular integrals, we have some problems of orthogonal surfaces. We have any given family of surfaces given in this form. A vector normal to the surface is given by gradient of the function involved with x component partial of f with respect to x, y component partial of y with respect to y, and z component partial of f with respect to z. And you require this to be perpendicular to some other surface, that is z is equal to phi xy. And the normal to this required surface is partial of phi with respect to x, partial of phi with y, partial of this whole function equation is with respect to z minus 1. Now, 2, 1 and 3 are required to be orthogonal, for which 2 and 4 vectors normals to 1 and 3 should also be perpendicular. And perpendicular condition is u1 v1 plus u2 v2 plus u3 v3. So take the dot product of this and this, and you get this. And we find that we have function of partial derivative of f with respect to x, which will be function of x by z, partial of f with respect to y, which will have a function of x, y and z. And this dou phi by dou x, dou phi by dou y, they become pq. And this also involves x by z. So that is taken as a function on the right side, and we obtain this function. This differential equation, whose solution will be the required orthogonal surfaces. So one problem, let me discuss quickly. This is the function given, and we want to find out system of surfaces that are orthogonal that also pass through this curve. So is constant is equal to fxy z की form में लिखा, partial with respect to x निकाला, with respect to y निकाला, with respect to z निकाला, and standard equation linear partial बनाई, auxiliary equation लिखी, and from auxiliary equation first two fractions dx is equal to dy because denominators are exactly same. So x minus y is equal to c1 is the first independent solution. And if we multiply by 3z plus 1 throughout in the denominator, so 3z plus 1 cancels from here, and 1 power cancels from here, and that goes above. Now, multipliers are used x, y. So x, y, and this. And that will give me the denominator xz, yz, and this multiplied to this, 3z plus 1 cancelled out, and minus zx minus zy remains. So the denominator becomes 0, so the numerator is also 0. And that makes the numerator integrable. So we integrate that to get